If we plot this function, and here I'm plotting it on this plot that I've drawn here, and before plotting this function, just want to point to your attention to the fact that theta equal to 0, so this point is this line that I have here. Theta equal to pi over 2, which is this line here, is exactly this line at the middle here. So that's my theta equal to pi over 2. So this is theta equal to pi over 2, theta equal to 0 here. And the front of the object, the stagnation point that I have at the front, is theta equal to pi, which is shown there. And if you recall, the convention for theta is again very much like any other polar coordinate you choose, is theta is increasing in this direction. If I plot 1 minus 4 sine theta squared, at theta equal to pi and theta equal to 0, I get plus 1 because sine is 0. And the minimum value of this function happens when sine is maximum, which becomes equal to 1 at pi equal to 2 for theta. That would give me 1 minus 4, which is negative 3 as a minimum. So if you plot this function, it's again a symmetric function with respect to front and back of the object. And it's a trigonometric function that goes very much like this. So it is basically going from 1 to negative 3, again rising back in a symmetric manner and going all the way to positive 1. Now, this is the theoretical prediction. So this is the theoretical prediction, and that's basically coming from this calculation we did for Cp as a function of theta. So I write this here, Cp as a function of theta. That's the plot that we have. However, you also, if you recall, we showed that experimentally you can also measure this pressure coefficient. You can measure the pressure around the cylinder that you have put in a wind tunnel. You can drill multiple holes at different angles around the cylinder. By pitot tubes, you can measure these pressures at a relatively high speed flow. And what you will see is experimental results that are like this dashed magenta line. So they agree almost perfectly with the theory in front of the object. However, when you reach the back of the object, there is something unusual happening at a certain angle. And then Cp as a function of theta becomes constant after that angle. So this is what I would say experimental results. And we discussed extensively in the class. So if I just try to, for example, your experimental data as star points would follow something like this, that are everywhere agreeing relatively well in front of the object with the theory, but in the back of the object or back of the cylinder, they deviate substantially from what the theory is predicting, which is the green line. And this was the idea that we set and discussed as a separation of the flow. And to really understand this, we need to think about what will happen to fluid elements as they are taking this trajectory around the cylinder. As they start their trajectory from theta equal to pi, they are sitting at a point that has the maximum pressure, that's the stagnation point. And their journey from theta equal to pi to theta equal to pi over 2 can be probably represented by this blue arc or blue trajectory. And at the same time, their journey from the other side, which is theta equal to pi over 2 to theta equal to 0, can be drawn or plotted with, for example, this white trajectory. Or maybe for clarity of colors, I can use a different color. I can maybe use yellow color here. So I can actually show this as yellow. So fluid elements really take this trajectory from pi. They come to pi over 2, and then they continue go to theta equal to 0. As they are taking this trajectory, they are really riding on this pressure distribution. From theta equal to pi over 2, they are always feeling a higher pressure behind them and a lower pressure ahead of them. That's very much like if you were thinking of a fluid element as a small ball sitting on top of a well. That's very much like the downhill path, because you're going downward. You really don't need to worry about energy that much, because you are always going to points that have lower height than your previous height. So you will actually easily move from this point all the way to theta equal to pi over 2, which is very much equivalent to the very bottom of this well. And this is relatively easy because you have some potential energy that is here, and you are going to lower potential energy, and all the potential energy is getting converted back to kinetic energy, but things are okay, and you can do that. Now, we know that in ideal systems, from what you have learned in physics, once your potential energy comes to a maximum kinetic energy, is converted all the way to the kinetic energy, you do the opposite on the other way around. You use this kinetic energy that you have gained, and then you convert it back to potential energy and move all the way back to this point. But I'm going to draw this point like a dashed trajectory or dashed line, because this would be the ideal path. If your ball was rolling on this well, your kinetic energy becomes maximum here, then you convert all this kinetic energy back again to a potential energy equal to your initial potential energy, and you raise your elevation back to the initial height. But we all know that in reality this doesn't happen. We often see, when we do this experiment, rolling balls stop a little bit short of gaining their initial height. They stop somewhere like that. So in reality, you really don't see this yellow transition go all the way. It stops short. And the reason for that is the fact that in real systems, we have the friction. The conversion of the potential energy into kinetic energy, and then kinetic energy back again to potential energy. This conversion will not happen in the exact manner that we would like, or ideal manner that we would like it to happen. There's quite a bit of kinetic energy that will be dissipated due to friction. As the ball is rolling on this surface, there's a substantial friction, and that friction really is what is setting the difference between height of these 2 points. So instead of going all the way back to this original height, you actually stop short, and this difference in height is what is known as energy loss due to friction. Exactly the same scenario happens to fluid elements here. They are moving with the pressure behind them higher, and this pressure behind them higher helps them to gain more and more kinetic energy. They had zero velocity here. When they reach here, they have maximum velocity or maximum kinetic energy here. If you look at the expressions for velocity, you can actually confirm that. Then on the way in the back of the object, when they are going from theta over pi over 2 to theta equal to 0, the opposite conversion should happen. The kinetic energy of fluid elements, which is maximum, should be converted into a pressure. So it should come all the way back and get converted back to maximum pressure when it reaches here. If the system was ideal, this conversion of energy from pressure to kinetic energy back again to pressure would happen in an ideal system. That's the whole idea of Bernoulli equation. But as we know, when you are a fluid element very close to the object, there is the effect of viscous interaction with the wall, or the boundary layer that we discussed in this module. So you will inevitably lose quite substantial amount of energy due to viscous friction. That loss of energy would mean that at some point, the fluid elements do not have anymore enough kinetic energy left to convert it back to the pressure. So there's a point that they have lost all the kinetic energy they had to both pressure and viscous friction, and they cannot really go anymore against the pressure gradient that they are moving, because in front you are going in a favorable pressure gradient, pressure behind you is higher, so you are pushed forward, but in the back of the object you are going against the pressure gradient, so you have adverse pressure gradient. You have to overcome pressure in front of you that is higher from pressure behind you, and that's the point that separation happens. Fluid elements run out of energy. Their energy has been dissipated due to friction. They don't really have enough or what it takes to keep their trajectory close to the object, and they prefer to leave the object and get separated. And that was the idea that we said, and we showed in visualization, that flow in wind tunnels, when you look at flow past a cylinder, you often see that it goes really smooth in front of the object, But behind the object, you see all sorts of very, I would say, formation of vortices or separation of the flow, and the fact that flow really here has a hard time following the shape of the object. We have discussed this extensively in our examples in the lecture videos that you have seen in the class. But I just wanted to mention that this is the main difference you often see between ideal solutions that come from potential flow and real experimental measurements that up to a good point they agree relatively decently, but a lot of times when you have phenomena such as boundary layer or separation, you see a deviation between potential flow and real measurements. And that's why a subject called boundary layer theory can help us to understand these differences, understand this mismatch between these two, and will help us to bring these two together in a rational framework that we will discuss in the next videos.